Testing, testing. Okay, mic seems to be working. Hi, I'm live, and I'm alive. I think it said that I haven't streamed in 2 weeks. I think, like 14 days or something. What? Yeah, life happens. I'm good. Let's do some learning. Yeah, let's not delay the inevitable. Right. So for today, I mean, obviously I've forgotten everything. That's not even a question. Like, that's super normal. I think my memory is like of 2 goldfish, not just one, because otherwise I would forget things faster, or I wouldn't remember useless things. So I think I want to start here instead of here, even though my love for unigrams is unmatched. I still think I would like to start here because it's the beginning of the lecture and it's about fine-tuning and instruction tuning. I'm not the biggest fan of instruction tuning, to be frank. But it says starting with fine-tuning, even, yeah, okay. Multitasking, fine-tuning, and instruction tuning, parameter, efficient fine-tuning, instruction tuning datasets, synthetic data generation. Fancy. So yeah, I'm gonna start with the fine tuning and see where that goes. If I feel like it, I will go back here. I'm currently feeling like starting here. And since our professor's head is at the top, I can do this. Yeah, it was under Karpathy's head that would get hidden by my character avatar. Let's see if we can hear him fine.
Yeah, today I'll talk about fine-tuning and instruction tuning. So this is kind of the first step in the pipeline of steps that people use to prepare models to be ready to be used as chatbots, like, what you...
Why are we, okay. I have expectations of it not only being about chatbots. Please don't let it only be about chatbots. Okay. Like, this is NLP, and NLP that isn't always just text. I'm gonna be really not smart and just say like it's 80-90% text most of the time. But OCR is technically NLP. So, because I remember Fast AI talking about OCR. Oh, but that was general LM. Huh. LM? ML, machine learning. Brain, where are you? Play.
You see in ChatGPT or Gemini or whatever else you want to be using. And what this basically takes advantage of is that...
Are we talking about things that are not just NL chatbots? I like the word plethora. Okay. Okay. I don't know why I'm interrupting him.
We have many, many different tasks that we can be solving in the NLP, and each requires different varieties of data. So up until this point, we've talked a lot about the varieties of tasks that only require text, such as language modeling. And then we also have other...
Hi. Hello, what's up? Long time no see. Yeah. I mean, I haven't streamed for 2 weeks, so it has been a while. How are you? I hope everything is good on your side. Thanks for stopping by.
Varieties of tasks that require only naturally occurring data. So like data that we don't actually have to create by hand. And or that we don't have to create by hand for the purpose of training like language models or NLP models. And this includes stuff like machine translation. And the reason why we have lots of machine translation data.
Oh, alhamdulillah, alhamdulillah. Inshallah, things will be good. Thank you. Yeah, overall pretty good. I miss learning. I mean, technically, I was busy enough not to have time to learn the past week, but I am technically always learning. Even if I'm watching silly videos, that's also learning because they're not in my native language. So that's technically learning. I'm sure you've heard this, but I don't know. Forgive me for not remembering, but there's this, I think it's a hadith that says, if you don't, like, if your days are the same, then it's basically like a sin because you are hurting yourself. But I think, astaghfirullah, what's wrong with me? Anyway, learning something new every day is something that should happen. Otherwise, your days will be the same in a way. So I take that to my heart. And watching YouTube videos might be a part of the learning. Maybe. I hope so.
It is people do translation anyway, even if we didn't have like ChatGPT or Google Translate or something, people would be doing translation, and a lot of this data can be used to train models.
True. Okay.
Then other things are hand labeled data. And so this is like for a lot of things like question answering or other tasks that you need to create data like named entity recognition or stuff like this. That data really mostly isn't naturally occurring. So we need to go in and actually create it by hand in order to do training. So like one of the interesting things about, the whole paradigm of training language models over the past several years is that we have been remarkably successful in getting models to work at a very large number of tasks by training only on text. So,
Right.
We trained something like Llama, or we trained something like the early GPT models that were trained only on text without very much supervised training data. The reason why is like what I mentioned last class, which is like actually a lot of data.
Hi, JSS, what's up? Hi. Back. This is my comeback.
Data on the internet just occurs in this form anyway. So we have.
It needs to be noted that I have a new chair right now. Yes, and I don't know how to sit while streaming. I will figure that out.
Have things like phrase books that appear online. And these phrase books weren't explicitly created as machine translation data or translation data even, but they appear online. And there's actually
pretty good. Health is good. Life is okay. She's, alhamdulillah, everything is good. Yeah. Oh, what did I do? Okay. Yeah.
Actually a paper that examines this.
I thought
that I didn't cite in the slide.
Yeah, okay. There are different types of tasks and they require different types of data. All right. These are, what would I call these types of data?
But it's a kind of interesting paper from ACL this year where they find that despite the fact that there's a language model that was trained on just, random data from the web, they found over 30 million translation pairs across at least 44 languages in this data that was just like straight from the web, not, explicitly for translation. Wow. And so there's lots of other examples of this, question answer pairs from FAQ pages on sites or other things like that. So, but anyway, yeah, getting back to the original thing here, in many cases, your models will have already been exposed to some data. There's some naturally occurring data that you can harvest and curate in an appropriate way. And then sometimes if you really want models to do something well, you can do them later, but that's very expensive and you're not going to be able to create them. So one very funny thing is I was playing around with GPT for translation, and I asked it to translate from English to Japanese. And it did really well most of the time.
I would also like to note that most of the times he brings Japanese as an example because I think he speaks Japanese. And I I feel him because I think most of the time I bring Korean or Arabic as an example because that's the languages I know.
It did, very good translations on English to Japanese and like 900 out of the 1,000 examples. Sometimes it just got it wrong because it's not a perfect translation system, but every once in a while it would translate into Japanese, which is.
It's not only translation, like recently I needed a phrase like that doesn't make sense to translate word by word. And I was like, what's the equivalent of that in another language? Not like, how do you translate it? Because if you say, like, what is the example? Help. Help. I can't think of it. Think of an example. No, wow, brain, what's wrong? Anyway, figures of speech sometimes you use cannot be translated and stuff like that, and you can ask for equivalents, which is pretty cool. I mean, I know people know how to use chatbots, but still. Okay.
In Japanese characters, and then it would translate into Romanized Japanese, into like the pronunciation. So no Japanese translator that you ask to translate into Japanese would ever do that. That would be like extremely unprofessional, right? You're saying, please translate this into Japanese for Japanese speakers. But why would GPT do this? Anyone have any ideas?
Huh.
Yeah.
But GPT is pretty good at writing in other languages. Its Arabic is great. Its Korean is great. That's the ones that I've tried. Why would it give us Romanized? I never use the word Romanized. I just use Latin. Should I start using the word Romanized? Because that's how it is on the internet? I don't think so. Has it been trained on, wow, this is a really specific example, but anyone who listens to K-pop, there are way too many Romanized versions of lyrics. I prefer translations to understand what's happening, but there are way too many Romanized lyrics. So is it trained on that? Now I'm curious. I want to train something on Romanized lyrics. They're everywhere. There are so many.
Yeah, someone on the internet did it that way. So a lot of the times when you have incidental training data on the internet, it would be from like phrase books of people who are trying to teach Japanese, for example. So every once in a while, like GPT got the idea that it should be translating like it did in a phrase book for Japanese learners as opposed to, like actually English to Japanese translation. So the problem is if you're learning only on this language modeling based text, you might get exactly what you want, but every once in a while you'll get something completely crazy that you never expected to happen. So that's the problem with just relying on base language models when we're doing training.
What happened?
So all the methods that I'm going to be talking about here fall under the class of multitask learning. And so multitask learning is training models to do well on multiple tasks at once. Just to give an example, you could have this as an example, and you could be doing language modeling on it. You could also be training a model to do tagging on it and other things like this. And exactly how you do this can be different. But the important thing is that you have some shared parameters between the models that are trained on all tasks. And if you're just training a big language model, then you'll probably be sharing all of the parameters. If you're training something like BERT, or like you're pre-training and then fine-tuning. You might train the body of the model on multiple tasks, but have a separate classification hub for different tasks. So there's different ways you can do that, but the basic idea is that you need to have lots of shared parameters. One easy way to do this, the very simplest way to do this, is to train the model and sample one mini batch for one task, another mini batch for another task, and just alternate between them, or alternate between them and sample 4 from one task and 1 from another task. So
if we sample based on tasks, are we training the model on all of the tasks? Is that why it's called multitask? But like, is one model multiple tasks, not bajillion models for bajillion tasks? I prefer specific models. Okay, ChatGPT is not a specific model. Yeah. Okay. Oh, Whisper is also not a specific model because it can do transcription and translation. And they said the fact that it can do translation makes it a good transcriber. Okay. Cloud Sonnet also. Yeah, I've started to fall in love with Cloud Sonnet. Am I saying it correctly? Sonnet, maybe. Not saying Sonic the blue thing.
So it's often as simple as that. Or you can just, or you can just mix all of the data together. So if you're doing
the hedgehog, don't sue me. Okay.
Like text, everything is text-based, then you don't even need to worry about mini batches.
Okay.
Cool. So separately from this, pre-train and fine-tune. So in pre-train and fine-tune, you first train on one task and then on another. And the way this works is you first train, for example, a language modeling objective. And then after you're done training the language modeling objective, you train on something else like tagging.
Oh, we're going to go through them and then talk about them in detail. The base model doesn't have to be something you've trained. It can be something that's trained by a huge company, which is, they have money and resources, and you're the one that does the training at a smaller scale for the fine-tuning.
And there's several reasons why you might want to do this. Does anyone have an idea about why you might want to do this?
I just said why.
As opposed to something like standard multitask learning, where you do both of them at the same time. This is a straightforward question.
Resources.
When I say straightforward, I don't mean easy. I mean not a trick question.
Oh.
Any ideas?
Money.
Okay, how many of you have trained a 70 billion parameter language model from scratch?
I mean, I did it yesterday, but
I see somebody say maybe, so that's actually pretty impressive. But why not?
Money.
Yeah.
And time and resources and knowledge.
Yeah, it's unbelievably expensive and a waste of resources. Yeah. So like if everybody was doing it, it would be a waste of resources. So we actually benefit a lot by a very small number of people doing this pre-training, and then the rest of us doing, fine-tuning on a smaller amount of data. So if you were doing all the multitasking from scratch, then that could be a waste. Does anyone have an idea why you might not want to do this?
Base models. Base model does not exist for your extremely specific task, maybe. Or base model is only in a different language and you're trying to do it for another language. Not that this happens anyway. All languages have resources equally. Oh, that was me being mad.
Actually, there's some other reasons why you might want to do this. Another reason why you might want to do this is, for example, if your pre-training data is big and messy, like, for example, if your pre-training data is all of the internet and the internet contains like lots of toxic text and text that's in a format that you don't want, you can still train on it and learn from it. But then fine-tuning can, make your model safer or remove
specify it even
like that as well. So does anyone have an idea why you might not want to do this?
Oh, hello.
This is a trickier question.
Mutahar? Why did I read it as Muzaffar first? Hi, hello.
Any ideas?
My idea was...
Or to put it in a different way, why you might want to do standard multitasking instead of this. Yeah.
The base model does not suit your fine-tuning?
Yeah. So if you don't have much tracking data, for example, then you might consider like doing the
Yay! Wait, is it Muzaffar? No way. Mutahar. Now I'm self-conscious. Hello, welcome to the stream.
So if you have lots of tagging data, I think yeah. So I think you're basically, this is a good point. So if you don't have lots of tagging data, you might have much more language modeling data than you have tagging data. So it's a better idea to train more on it. That is true, but you could sample like 99 mini batches of language modeling data and one mini batch of training data, or 999 of language modeling data. So it's a good, you're going in a good direction. Anything else?
No.
Yeah.
pre-training data certain biases you already built.
So if your pre-training data has certain biases, you might inherit it. Do you think that's a bigger problem with pre-training or pre-training and fine-tuning or standard multitasking?
That's everywhere. Biases.
Yeah.
I think the reason why you might not want to do this is perhaps you could lose some of the representation that exists in the multi-time data sets.
So you might lose some of the information that exists in the multitask data set. I think that's pretty close to what I'm going to say. So let me just go ahead and give the answer. Hopefully everybody had time to think about it. But this is a paper that we wrote previously, and basically one interesting thing is that you actually do better. You do better if you train on multiple tasks at the same time. And our hypothesis about why the reason you do better on the end task that you finally want to do well on compared to pre-training and fine-tuning.
Okay, but if you don't have resources and well, resources includes money, then you can't. Why did this just become very British? Sorry. But pre-training plus fine-tuning. The blue is
And our hypothesis about this, which I've also seen a few other works, is if you pre-train on the task that you finally want to solve, while you're also solving the language modeling task, essentially the model is learning representations that are useful for both at the same time, as opposed to if you're training on the language modeling task, it will be learning representations that are useful for the language modeling task, but not necessarily focusing on the representations that would be useful for the end task. So, like, for example, if you're jointly training on sentiment analysis and language modeling, the representations that are useful for sentiment analysis will be more salient in the model, essentially. And so that will be particularly a problem when there's when you have a varied optimization landscape and multiple local optima, and the language modeling might not get you into the global optimum that you want for the end task that you're solving. There's also another interesting paper from Anthropic.
This is local optima and global optima, really? I don't know why I didn't say that. Anthropic, really? What was it that I needed to say? Okay. Let's listen.
More recently than ours, that shows something a little bit similar, specifically from the point of view of safety training. And they demonstrate that if you start out by having a concept of safety early in your training, you're able to reach better better final results than if you start safety training after you trained your model for a while. So and this is
Okay, that actually makes sense. If you start off with a specific task, it's better than fine-tuning on a specific task. That's basically what it's saying, which but not everybody has the resources.
Particularly for things like toxicity. So there are downsides to pre-training and fine-tuning, but
But honestly, okay, this one's huge. It's not that bad. Like the amount of resources this one requires versus this one, I don't know how big is the difference, but like these two doesn't seem that much. So you get similar results with way less.
upsides of, spending lots of compute once and then fine-tuning for lots of different, downstream tasks is like large enough that that's still the standard nowadays. Any questions about that?
No.
Okay, cool. Let's move on. So we talked about prompting before. I'm just going to go over that very quick, just say it for completeness. But when we're prompting, we have an encoder. We train it on language modeling or whatever else, but then we freeze it and then we specify the task by a prefix like this. And what instruction tuning does is instruction tuning is like a combination of fine tuning and prompting. And so what we do is we pre-train and then sorry, I guess I failed to update the figure here. So this is just the figure for fine tuning. So normally what you do is you
instruction tuning and prompting. Prompting is basically you're talking to the thing, and instruction tuning is that you like, I don't want to use the word, but I will, but like demand something. Like do this in that way. That's what instruction tuning sounds like to me. Let's see if I'm wrong.
Have a prompt for one task, a prompt for another task, a prompt for another task. And then you train your model specifically so that it does good completions of those prompts. And I'll give some actual examples of that later. So yeah, sorry, the figure, I will need to fix that.
Yay. Thank God. So this was a overview, and now we start with fine tuning. Kazi, how far will it go? I don't know why I'm doing accents. Oh, wow. This is continuing. Oh, wait. NLP tasks? This is like 30-something minutes, huh? Okay.
Just taking a note.
Take your time.
Okay, so we haven't really covered fine-tuning yet in general. So I want to talk a little bit about what we do for fine-tuning, and particularly what we do for fine-tuning very large models, because I think that's what a lot of people want to do nowadays. So for full fine-tuning is relatively easy. What we do...
full fine-tuning. Why do I not know about this?
Easy conceptually, hard in practice. So what we do is we simply continue training the language model on whatever data we want to be fitting to. So this could be like translation pairs, it could be question answering pairs, it could be anything else like that. But the issue is, depending on the method that you're using to optimize your model, the method can take lots of memory, and also in some cases it can be relatively unstable compared to some other alternatives that I'm going to talk about in a bit.
Really?
And just to give an example, training a 65 billion parameter model, which is the largest version of Llama 1, with 16-bit mixed precision actually takes much more memory than you would expect if you haven't done this before. So if you look at the amount of memory required for holding the model in the first place, if we have 65 billion parameters times 2,
I mean, that's why we have streaming, no? Does that help? I mean, not the streaming I'm doing right now. The streaming a model from an existing cloud source.
That would be 130 gigabytes of memory already. So that's already a lot of memory, right? But if we want to do, if we want to hold both the parameters and the gradients of the model, obviously we need to double the number of points here. So we also have 130 gigabytes for the parameters. Sorry, for the gradients. Then we have the optimizer, and this could be an optimizer like Atom. If people remember, Atom has first moments and second moments, so it has the mean and something that looks like the variance. And these, at least according to this paper from 2019, needed to be stored in 32 bits. So these needed to be stored in 32 bits of memory, because if you store them in smaller amounts of memory, they would have underflow issues, overflow issues, and basically the numerical precision would destabilize your training. And then in addition, the parameters also needed to be measured in 32 bits. So you needed a 32-bit copy of the parameters. This is just the parameters of the model. And then separately from that, you also need to do the forward and backward passes. And so if you do the forward and backward passes, depending on how big your batch size is, how many tokens you have in each instance, this could take, significant amounts of memory too, like 100 to 200 gigabytes. So overall, this would take around 1,000 to 1,400 gigabytes of GPU memory in the very naive scenario. And this is not that great. Now, this paper was written in 2019, and there have been some advances since then in optimizing models. So to give some examples of things that can be fixed, previously, when we were using FP16, so like the regular ANSI floating point numbers like we use on our CPU, this was it. You needed 32-bit integer, 32-bit floats to make this stable. Now it's pretty standard to use BF16, brain float 16, like I talked about earlier in the class. And because of that, this can be made more stable. So you can reduce this to things like 2 bytes instead of 4 bytes. We can also, if we do that, we don't need this extra copy of the parameters. So we can get away with about 8 bytes per parameter we want to optimize, but that's still, a lot of memory. That's 130 gigabytes of memory for a 65 gigabyte model. And the forward and backward passes still take space as well. So basically what I want to say is full fine tuning is pretty memory intensive. And if we look at how big a standard...
I'm curious if we can compare it with normal training. Full fine tuning versus a normal training something from scratch. Like, yeah, it's resource intensive, but it's not as if you're starting from scratch. But let's see what are better ways.
GPU is. I took some specs here. The memory is just the memory on the GPU. The cost, I did a very unscientific thing of Google the price on Amazon and take a look at the price of the GPU here.
Okay.
And then on the right side, this is the types of cloud machines that support these GPUs. And in this class, a lot of people are using Google Colab, I think, for your current assignment, and soon we'll have AWS credits for everybody, so you can use AWS machines. So if you look at the GPUs that are available, we have things everywhere from 24 gigabytes, 32 gigabytes, 40 to 80 gigabytes, 48 gigabytes, or on your Mac, the GPU and CPU memory is shared. And basically what we can see is that there's no GPU with 130 gigabytes of memory, right? So none of them can do this with a single GPU. There's also a bunch of other hardware options like AMD GPUs, Google GPUs, special purpose training things like Cerebrus, AWS Trainium, et cetera. But I think for the purpose of this class, you're probably going to use standard hardware like this. So anyway, like that model will not fit on any, or that fine tuning will not fit on any GPU that you have available to.
Oh,
Any questions about this? Yeah.
What are the other like special purpose hardware used for?
So a lot of these are created specifically for training neural networks. So they're like really, really good at the things you need to be training neural networks for.
Mhm.
I haven't actually used any of these, so I can't like endorse or disendorse any of them, but they're made to be like really good at training transformer language models or like the specific thing that everybody wants to train. The disadvantage is if you start wanting to be like a little bit more creative than what they imagined, it might not support that. So that's also a problem with TPUs. TPUs are very good at certain things, like they're very good at like batched large operations, but they're less good at nimbly executing dynamic computation graphs and stuff. So from that point of view, I think most people in research still use GPUs.
Thank you.
Okay.
One thing I should mention is the AMD GPUs. A lot of people have started using them in like 2023, 2024. Like I think previously it was kind of a NVIDIA one horse race, but I've heard more and more people using AMDs, and they're not price gouged quite as much. So,
Huh.
Any other questions? So training models, like if they're pre-training models, they're using like 1,000, 2,000, 4,000 or something. Like Meta just announced that they got
Meta?
350,000 H100s or something like this. And in case you are too lazy to calculate, that's about 10
350,000. How much physical space does that take?
to $20 billion. It's a lot of money.
That's money that you can laugh at. Whoa.
And I'm sure not all of them are being used to train a model. A lot of them are used for model serving and stuff like that. So, but there's a reason why we're not all pre-training models, right?
Absolutely. Also, question: are some of them being used for usage, model usage, even?
It's a big effort. It's very expensive. So.
Mm.
Cool. Any other questions? Cool. Okay.
Yes.
So how can we overcome this? The first way we can overcome this is using things like multi-GPU training. And one solution is just to throw more hardware at the models and distribute the models
How do I throw it exactly?
over multiple places.
Mm.
And the canonical or the most well-known version of this that still many people use when they're pre-training or fine-tuning language models is something called deep speed zero.
Mm-hmm.
And the way deep speed zero works is it works by partitioning optimization over different devices. And so there's different stages of deep speed. The first one is this one right here. And this says 2 + 2 + k, where k is the size of the optimizer state that I had here. So 2 bytes plus all of the bytes required for this. And the blue is the first two, the orange is the second two, and the green is the third one. And so basically the baseline is you hold all of these on each GPU. The second thing is you partition the optimizer state across different GPUs. And because optimizer state is generally larger or at least as large as all of the others, this can reduce memory requirements significantly. So this went from 120 gigabytes for whatever model they were doing there to 31 gigabytes based on So this was a 7.5 billion parameter model. So the
Oh, this means parameter? I was like, what is this Poseidon thing doing here? Poseidon? Is it Poseidon's? Call it Trident? I don't know, but it looks cool.
and they had, let's see, yeah, and they had 64 devices. So they went down from 120 to 31. This is with 12 bytes for their optimizer state, like I said here. But actually we can get away with 4 bytes for the optimizer state. So actually you can train a 7 billion model reasonably easily on, 1 or 2 devices.
With a B.
1 or several devices now with this. So this is called stage 1. This is partitioning the optimizer state. Stage 2, this is partitioning the optimizer state and the gradients.
Mm-hmm.
The optimizer state is actually, doing the optimizer state is actually relatively like harmless. It doesn't slow down too much. Partitioning the gradients gets a little bit more tricky because you start having to move things between devices a lot. And then if you do this for the parameters, you can do even more. So you can get it down to like ridiculously small values here, but this is going to be very expensive in terms of moving things around so that you can calculate your gradients appropriately. So I'd say that by default, if you can go to deep speed with like stage 1 or stage 2, you can spread this up across different devices and trade models. Yeah.
It's just a general question that multi-GPU training, does your central device that is doing like the other question? I think that does it need to have at least
Does your central device can basically be your CPU. When you say multi-device, sorry, do you mean multi-GPU or do you mean multi?
Like,
okay.
So if there, let us say on the top, your CPU needs to be able to handle that.
I don't think so. I mean, it depends on the implementation, but not theoretically anyway. And I can deep speed handles that for you. Yeah, otherwise you'd have lots of trouble like getting the machine that had, 1,000 gigabytes of memory.
Mm-hmm.
So yeah, I would suggest definitely using something like deep speed, but actually a lot of libraries use deep speed under the hood also. So things like HuggingFace Accelerate, GPT NeoX, other things like this, they all interface. Many of them interface to deep speed or something similar to it. So whatever library you're using for training like this, you can do. I don't have a list, but there's a whole bunch of them. You can either use deep speed, things like HuggingFace Accelerate or TRL. I think we might have a TRL recitation later. Also, I haven't used it myself or worked with people who've used it, but Axolotl, a lot of people are using. So maybe we could come up with a list of those later.
Okay. Cool.
So
do I pause here? Because it's a different type of fine tuning, and it has a lot. Like LoRa goes up. Like, yeah. Okay. LoRa goes too far for me to comfortably say I can. Like I don't know. Do I have another 30 minutes? I don't think so. I guess I have enough energy for this. Oh, okay. Even if I have another 30 minutes, that doesn't mean I want to do the same task, the same thing. So, should we start by, yes, we're still, in the tokenizer library. I'm surprised it's taking us more with the tokenizer library, but also not really surprised. It's like, it's a course, it's supposed to take time. Yeah, we're at the unigram tokenization. So I'm gonna start. Let's see if I have the energy to finish it. So The unigram algorithm is often used in sentence piece, which is the tokenization algorithm used by models like Albert T5. I like T5. MBART, Big Bird, and XLNet. Okay, let's see this video. By the way, it says you don't have to take this, but you can if you want to. And I want to. Ooh, this is an 8-minute video. I'm surprised.
In this video, we will study together the Unigram language model subword tokenization algorithm. The overall training strategy of a Unigram language model tokenizer is to start with a very large vocabulary and then to remove tokens at each iteration until we reach the desired size. At each iteration, we will calculate a loss on our training corpus thanks to the Unigram model. As the loss calculation depends on the available vocabulary, we can use it to choose how to reduce the vocabulary. So we look at the evolution of the loss by removing in turn each token from the vocabulary. We will choose to remove the %, which increases the loss the less. Before going further in the explanation of the training algorithm, I need to explain what is a unigram model.
Yeah. I think I don't know about the unigram loss thing. Do we just take away vocab? I didn't know that.
Unigram language model is a type of statistical language model. A statistical language model will assign a probability to a text considering that the text is in fact a sequence of tokens. The simplest sequence of tokens to imagine are the words that compose the sentence or the characters. The particularity of Unigram language model is that it assumes that the occurrence of each word is independent of its previous word. This assumption allows us to write as
Yes. You sort of lose context in n-gram language models.
the probability of a text is equal to the product of the probabilities of the tokens that compose it. It should be noted here that it is a very simple model which will not be adapted to the generation of text, since this model will always generate the same token, the one which has the greatest probability.
That's true. There's a good chance of reproducibility because things don't change. By the way, I'm saying these things with zero authority. I could be wrong. What is it that I wanted to say? There was something I wanted to say, which is you could work within a context, but the probability is coming from a statistical model, so it's not going to change.
Nevertheless, to do tokenization, this model is very useful to us because it can be used to estimate the relative likelihood of different phrases. We are now ready to return to our explanation of the training algorithm. Let's say that we have a training corpus with 10 times the word hug, 12 times the word bug, 5 times the word lug, 4 times bug, and 5 times dog.
Okay, that's funny. Also, where's lug? Wait, I read lug. Where's rug? Because the pug could hug a bug on a rug. There's my sentence. You're welcome.
As said earlier, the training starts with a big vocabulary. Obviously, as we are using a toy corpus, this vocabulary will not be that big, but it should show you the principle. The first method is to list all the possible strict substrings, and that's what we will do here. We could also have used the BPO algorithm with a very large vocabulary size, but for now, the strict substrings are enough. The training of the unigram tokenizer is based on the expectation maximization method.
Why does our vocab look like this? What did I miss? Are we splitting on character?
At each iteration, we estimate the probabilities of the tokens of the vocabulary. And then we remove the % of tokens that minimize the loss on the corpus, and which do not belong to the basic character, as we want to keep in our final vocabulary this basic character to be able to tokenize any word. Let's go for it. The probability of a token is simply estimated by the number of operands of this token in our training corpus, divided by the total number of operands of all the tokens.
Yep.
We could use this vocabulary to tokenize our words according to the unigram model. We will do it together to understand two things: how to tokenize a word with a unigram model, and how the loss is calculated on our corpus.
Okay.
The unigram LM tokenization of a text, HUG, will be the one with the highest probability of occurrence according to our unigram model. To find it,
HUG has the highest one?
the simplest way to proceed will be to list all the possible segmentation of our text, HUG, calculate the probability of each of these segmentation, and then choose the one with the highest probability. With the current vocabulary, two tokenizations get exactly the same probability. So we choose one of them and keep in memory the associated probability. To compute the loss on our training corpus, we need to tokenize, as we just did, all the remaining words in the corpus. The loss is then the sum over all the words in the corpus of the frequency of the occurrence of the word multiplied by the opposite of the log of the probability associated with the tokenization of the word. We obtain here a loss of 170.
Oh,
Remember,
that was the loss. I wasn't paying attention. Help. The opposite of the log? Why?
our initial goal was to reduce the vocabulary.
Okay.
To do this, we will remove a token from the vocabulary and calculate the associated loss. Let's remove, for example, the token HUG. We notice that the tokenization for HUG with the letter H on the tuple HUG is now impossible. Nevertheless, as we saw earlier that two tokenizations have the same probability, we can still choose the remaining tokenization with a probability of 1.10 minus 2. The tokenization of the other words of the vocabulary also remain unchanged. And finally, even if we remove the token HUG from our vocabulary, the loss remains equal to 170. For this first iteration, if we continue the calculation, we will notice that we could remove any token without it impacting the loss. We will therefore choose at random to remove the token HUG before starting a second iteration.
I was like, then what do we do if everything is the same? We just kill something randomly.
So we estimate again the probability of each token before calculating the impact of each token on the loss. For example, if we remove now the token composed of the letter H and U, there is only one possible tokenization left for HUG. The tokenization of the other words of the vocabulary is not changed. In the end, we obtain by removing the token composed of the letter H and U from the vocabulary a loss of 168. Finally, to choose which token to remove, we will, for each remaining tokens of the vocabulary, which is not an elementary token, calculate the associated loss. Then, we will compare this loss with them. The token which we will remove is the token which impacts the least the loss. Here is the token B. We had mentioned at the beginning of the video that at each iteration we could remove 10% of the token per iteration. The second token that we could remove at this iteration is the token D. And that's it. We just have to repeat these steps until we get the vocabulary of the desired size. One last thing. In practice, when we tokenize a word with a unigram model, We don't compute the set of probabilities of all the possible splits of a word before comparing them to keep the best one.
Okay.
But we use the Vtubing algorithm, which is a really much more efficient way to do it. And that's it. I hope that this example has allowed you to better understand the unigram tokenization algorithm.
I will say it confused me. I understood it, but also it messed with my understanding of n-grams. And now I don't know who I am anymore. I don't know what's my identity. I've become what a reference. Jackie Chan, when he says, "Who am I?" Is that the name of the movie? Wow, it's been a while since I've watched it. Alrighty then. Let's start with the reading. Can we see it? We should be able to see it. Okay. I'm not gonna use the mouse because it really makes my hand hurt. I'm sorry. I'm just gonna read it. Maybe I could do like a "this is where I am" sentence-wise. Okay, I'll do that. Compared to BPE and word piece, unigram works in the other direction. It starts. Oh, okay. The thing is, I've never killed stuff within my vocabulary. I'm like, I have a vocabulary. The end. It starts with a big vocabulary and removes tokens from it until it reaches the desired vocab size. There are several options to use to build that base vocabulary. We can take the most common substring in pre-tokenized words. For instance, or apply BPE on the initial corpus with a large. So we are doing the thing. Most common string, or apply BPE. We're doing something. At each step of training, the unigram algorithm computes a loss over the corpus given the current vocab. Then for each symbol in the vocab, the algorithm computes how much the overall loss would increase if the symbol was removed, and looks for the symbols that would increase it the least, meaning that would increase it the least. It would make sure that we have the smallest amount of loss. Increases the least is that's what it's supposed to mean. So the symbols have a lower effect on the overall loss over the corpus. So, what's with all the so's that I'm reading from air? Those symbols have a lower effect on the overall loss over the corpus. So in a sense, they are less needed and are the best candidates for removal. I have a question. Aren't things that have a smaller probability more useful within a corpus? Isn't that how language works, sorta? The more it's available, the less useful it is. That's my understanding anyway. And I know we are splitting things, and the splitting thing is what's it allows the removing. Because we can recreate stuff, no? Cario. Okay. This is all very costly. Yes, very costly operation. So we don't just remove the single symbol associated with the lowest loss increase. Lowest loss increase. It makes we don't remove a symbol that does not increase our loss, but the probability being P of P, hyperparameter you can control. Usually 10 or 20% of symbols associated with the lowest loss increase. This process is then repeated. We take a good percentage. What? Is this where it starts? I mean, ends? No? Why are you here? Repeat it until vocab has reached the desired size. Cool. Note that we never remove the base character to make sure any word can be tokenized. Is that what it means? We don't want to remove words? We're just... 진짜. I am very now. Now this is still a bit vague. You think the main part of the algorithm is to compute a loss over the corpus and see how it changes when we remove some tokens from the vocabulary, but we haven't explained how to do this yet. This step relies on the tokenization algorithm of a unigram model. So we'll dive into that next. This is our corpus. We have a hug and a pug and a pun and a bun and hugs. Okay. And for this example, we will take all strict substrings for initial vocab. See? Who agreed? Who decided on this? That's where my qualm is. Okay. We have the tokenization algorithm. My energy is draining by the second. I don't want to start it. If I start it, then I'm going to be... Okay. They say if you leave something halfway, you have a better chance of coming back to it. Meaning I want to come back to this tomorrow. Yeah. Let's see if tomorrow helps me understand better, because starting with a busy brain after half an hour here, I don't think I have the capacity to accept more. So, I think that's it for today. Yeah. I'm happy that I'm back, because I think I've said that a lot, but I will say it again. I enjoy learning on stream. I'm the type of person who gets distracted easily, and the fact that I'm learning on stream means I have some sort of responsibility to do it. And I like that. But, you know, I like that I can trick myself into learning. I mean, I am a lazy learner. I'll give you that. But I'm trying. Yeah, so I hope you learned something with me. And yeah. Yeah. I hope you have a lovely Monday. It's a Monday. Inshallah, good things waiting for us this week. Okay. I want to say Amin Ajmain for all of us. Yeah. I want to come back tomorrow and start from this unigram tokenization algorithm. And then maybe we can go back to the fine tuning. Okay. That's the plan. And there's a really cute bear. You can see. I think it's supposed to be a necklace, but also there's a really cute cat that you can't see, which I'm sad about. There's the cat. That's the cat. Okay, there's a bear and a cat. That's it for today. Yeah, see you next time. I'm gonna end the stream in 5, 4, 3, 2, and 1. Thank you.